Welcome. Take a moment to settle in without trying to find the perfect position. Turn the volume down to the point where my voice is only just audible, a little below what would be comfortable in daylight. Nothing that follows needs to be remembered or understood or followed to the end. You can fall asleep at any point and you will not miss a thing. Tonight we are going to talk about whales slowly, without hurrying. The oldest surviving descriptions of whales in the Greek language belong to Aristotle, who gathered what fishermen along the Aegean coast could tell him and set it down in his treatise on animals in the 4th century before the Common Era. And what he recorded there is more accurate than almost anything written on the subject for the next 2,000 years. He observed that dolphins and porpoises and the larger creatures he grouped with them do not take in water as fish do, but breathe air through a passage on the top of the head, that they bring forth their young alive rather than laying eggs, and that they suckle those young with milk. He noted that a dolphin makes a squeaking or groaning sound when lifted from the sea, and that such animals may be found sleeping at the surface, with the blowhole above the water. He set them apart from fish in his descriptive scheme, placing them among the blooded animals that bear live offspring, and he remarked in passing on a great whale whose mouth held not teeth but bristles resembling those of a pig, which is a reasonably exact description of baleen from someone who had probably never stood beside a living one. That clarity did not survive its transmission. The Greek word ketos, which passed into Latin as cetus, covered any very large sea creature without much regard for its anatomy, so that the sea monsters of myth and the animals of the fisherman's experience shared a single name, and later writers who inherited the vocabulary without the observations tended also to inherit the ambiguity. Pliny the Elder, compiling his enormous survey of the natural world in the 1st century of the Common Era, brought together sober report and traveller's rumour in the same paragraphs, describing the spouting of whales, their combats, their appearance off distant coasts, and their alarming size, with no strong method for separating what a sailor had seen from what a sailor had been told. He recorded an account of one such animal that entered the harbour works at Ostia during the reign of the Emperor Claudius, and was hunted there with nets and lances from boats in the sight of a crowd, a scene that reads less like natural history than like an entry in the calendar of Roman spectacle, and which has been discussed ever since by readers trying to decide which species the description best fits. Later writers of antiquity carried the material forward, with the emphasis shifting steadily away from anatomy and toward wonder. Oppian composed a poem on fishing in which the great sea creatures move through the water like moving reefs, and Aelian assembled short chapters on animal behavior in which whales figure as vast and vaguely benevolent presences. The habit of drawing moral lessons from animals was already established, and the whale, being immense and glimpsed only in fragments, was an unusually accommodating subject for that habit. A creature seen as a dark back and a column of spray, appearing and vanishing at intervals, leaves a great deal of room for interpretation, and the interpretations accumulated faster than the observations. The most consequential of them entered European thought through the Physiologus, a compilation of animal descriptions with attached spiritual readings that was assembled in Greek in the early Christian centuries and translated into Latin, and then into most of the vernacular languages of Europe. In it appears the creature usually called the aspidocolone, a sea beast so large that sailors mistake its back for an island, land upon it, drive in stakes and light cooking fires, whereupon the animal feels the heat and descends, dragging ship and crew into the depths. The moral was plain and was always spelled out. The whale is the deceiver, the island that is not an island is worldly comfort, and those who moor to it are lost. The image was too good to abandon, and it was copied for 1,000 years into bestiaries in Latin, French, English, and German, illuminated with a whale bearing a fire and a small ship on its back, and repeated in the Old English poem on the whale preserved in the Exeter Book, where the animal is given a name and a settled reputation for treachery. The same figure surfaces in the voyage narratives, most famously in the Latin account of the sea journey of St. Brendan, in which the travelling monks celebrate Easter each year on the back of a great fish that rises to receive them and sinks again once they have gone, and which in that telling is obedient and providential rather than malicious. Alongside these stories, the bestiaries carried other assertions about whales that were repeated without examination, that the animal's breath had a sweet smell which drew smaller fish into its open mouth, that it could not turn quickly, that it fled from certain sounds. Some of these notions had a distant root in something real, since the gaping mouth of a feeding baleen whale had certainly been seen, but the mechanism was misunderstood, and the tendency to explain a whale's behavior in terms of intention rather than of feeding or breathing runs through nearly all of the medieval material. Practical knowledge, meanwhile, was being accumulated by people who did not write bestiaries along the Norwegian and Icelandic coasts, in the Faroes, in the Basque ports of the Bay of Biscay. Communities had been taking whales, or making use of stranded ones, for a very long time, and the vocabulary they developed reflects genuine discrimination between kinds. The Norwegian dialogue on kingship and natural wonders, composed in the 13th century, known as the King's Mirror, contains a passage listing the whales found in the northern seas with attention to their size, their food, their oil, their disposition toward boats, and whether they were considered fit to eat. And although the list mixes the recognizable with the fabulous, the recognizable part is substantial. There are whales that strain small creatures from the water, whales with teeth that hunt seals and other whales, whales too large to be pursued, whales whose flesh was prized. Names of that kind, coined by people who had cut the animals up, were more reliable than the Latin encyclopedias, and centuries later some of them fed into formal scientific naming. The transfer of all this onto maps happened as the charts themselves grew more ambitious. Portolan charts of the Mediterranean concentrated on coasts and bearings and left the open water largely bare. But the printed world maps and regional maps of the 15th and 16th centuries had wide empty seas to fill, and filling them with creatures served several purposes at once: decorating the sheet, indicating that the waters were inhabited, and signaling the dangers of particular passages. The most influential single source was the great chart of the northern lands engraved by the Swedish churchman Olaus Magnus and published in 1539, which scattered across the seas between Norway, Iceland, and Scotland a population of spouting, tusked, bristled, and armored animals, each drawn with confidence and some with keys explaining their habits. He later expanded the material into a long book on the northern peoples, in which whales overturn vessels, are frightened by trumpets, and are distinguished from one another by features that sometimes correspond to species and sometimes do not. Because those images were engraved and printed, they traveled. Compilers of cosmographies and atlases copied Olaus Magnus's creatures onto their own maps, sometimes with the details rearranged, and the map of Iceland issued in the Great Antwerp Atlas of the later 16th century carries a crowded sea of them. Spouting animals labeled with names drawn from classical Greek, a creature with the head of a pig, others with long tusks or with manes. Read closely, the crowd sorts into two kinds of thing. Some of it is invention, or garbled report, or the borrowing of a lion's face for a body no one had seen whole. Some of it is recognizable, the double plume of a right whale seen from the front, the single-angled spout of a sperm whale, the long spiral tooth of the narwhal, the vertical breach and the raised flukes, all features that a person standing on a northern shore could actually have witnessed and described. What the early accounts consistently got right was that these animals breathe, that they spout, that they nurse their young, that they differ from one another in size and habit and diet, and that some of them may be taken for their oil and flesh. What they consistently got wrong was scale, intention, and mechanism, so that the whale was reliably drawn larger than any whale has ever been, credited with a wish to destroy shipping that no whale possesses, and understood to blow water from its head rather than warm breath condensing in cold air. Those three errors, the exaggerated bulk, the imputed malice, and the misread spout, would each take a different route to correction, and the earliest steps in every case came from people examining bodies on beaches rather than from readers examining books. A whale that came ashore changed the terms of the problem entirely, because for the first time the animal held still. Everything written before had depended on glimpses from a moving deck, on a back and a spout, and a set of flukes disappearing, on the memory of sailors and the retelling of that memory by men who had never left land. A stranded whale, by contrast, lay on the sand in full daylight and could be walked around, climbed on, counted against a man's height, prodded, opened, measured with a rope, and drawn from more than one side. The knowledge that came from beaches was therefore of a different kind from the knowledge that came from books, and it accumulated slowly, in fragments, wherever a coast happened to be inhabited by people who could write and draw. Strandings happened, and still happen for many reasons, some of them understood only in outline. Sick or injured animals drift inshore, old animals die at sea and are pushed by wind and tide onto a beach. Whole groups of some social species come ashore together on gently shelving sand, and in places where a shallow bay lies across a whale's path, the same stretch of coast receives bodies again and again across centuries. For the naturalists of early modern Europe, none of this could be arranged. The whale arrived without notice, in whatever season and whatever weather, often at some distance from the nearest town, and the person best placed to describe it was rarely the person best trained to do so. There was also a clock running from the moment the animal came out of the water. A whale is built to be supported on all sides by the sea, and on a beach its own weight begins to press the ribs down onto the lungs and to flatten the whole body out of its living shape, so that the outline recorded by an artist working on the third day is already not quite the outline of the animal that was swimming a week earlier. Warm, thick blubber holds heat, and decay proceeds inside the closed body more quickly than the cold weather outside would suggest, producing gases that swell the abdomen and eventually vent, along with a smell that carried inland for considerable distances and is recorded in almost every account we have. Anyone who wanted to know something exact had to work quickly. In a crowd, in the presence of that smell. The crowd was there for good reasons of its own. Blubber rendered into oil for lamps and for the treatment of leather and rope was worth money, and the meat could be eaten or fed to animals, and the great bones had uses in building and in the making of tools. And in the case of a sperm whale, the head held spermaceti and the gut occasionally held ambergris, both of which were valuable out of proportion to their bulk. Because a stranded whale was valuable, it was also contested. In several kingdoms, the whale was reckoned a royal fish, belonging by right to the crown or to a lord holding the shore, and the arguments over who might cut and carry what produced court records, receipts, and correspondence which survive in archives and which now serve incidentally as a register of when and where large whales came ashore. Out of the same commotion came a small class of printed images that mattered a great deal. Engravers in the Low Countries, working from sketches made on the spot, produced broadsheets of stranded whales in which the animal lies along the sand with the dunes behind it, and a numbered or lettered crowd arranged around it. Gentlemen on horseback, women with children, men on ladders, and men with knives, and often a figure holding a pole or a measuring rod against the flank. Those human figures are the useful part. They fix a scale that words alone had never fixed. And once a whale is drawn beside 40 recognizable people, it becomes difficult to go on believing in an animal that could be mistaken for an island. The caption frequently give a length in local feet, and while the units vary from town to town, the numbers fall into a plausible range, and the exaggerated bulk of the medieval whale begins quietly to deflate. The same drawings begin to record features that mattered for classification, though no one yet had a system into which to put them. The position of the blowhole on the top of the head, and whether it was a single opening or a pair, appears with increasing accuracy. So does the shape of the flipper, the presence or absence of a dorsal fin, the long pleated grooves of the throat in the rorquals, the fringe of horny plates hanging from the upper jaw in the animals we now call baleen whales, and the row of stout conical teeth in the narrow lower jaw of the sperm whale set against an upper jaw without any working teeth at all. Some of these were noted as curiosities, and some were misunderstood, but they were on paper, and paper could be compared. A few naturalists managed to reach a carcass in time and wrote about it as a body rather than a portent. In the middle of the 16th century, two French scholars, working independently, published accounts of marine animals that included dolphins and whales. And both of them were prepared to say that these creatures breathed air with lungs, bore live young and gave milk, and were therefore not fish in the ordinary sense, which is a conclusion drawn from a beach and a dissecting knife rather than from an ancient authority. Late in the 17th century, a Scottish physician gathered descriptions of whales stranded on Scottish coasts, including animals from the Firth of Forth, into a short book devoted to whales alone, and in doing so treated strandings as a source of evidence to be collected systematically instead of as isolated marvels. Keeping anything of a whale was harder than describing it. To obtain a skeleton, the flesh had to be removed, which in practice meant flensing what could be reached, then either leaving the remainder to the tide and the gulls, or burying the bones in sand or in a pit of earth for a year or more and digging them up again once the soft parts had gone. Even then, the bones were saturated with oil, and a large whale skeleton will weep oil for decades in a warm room, darkening the floor beneath it and complicating any attempt to keep it clean, which is why later museums developed elaborate methods of degreasing, and why the earliest displayed bones tended to be single elements rather than whole animals. Those single elements went in various directions. Ribs and jawbones were hung in churches and in town halls, sometimes as memorials of a remarkable local event, and sometimes without any explanation at all, and a jawbone set upright in the ground made a serviceable arch over a path or a gate, while a shoulder blade could be used as a table or a seat and a vertebra as a stool. As the memory of the stranding faded, the label drifted, and bones known to one generation as the ribs of a whale were shown to the next as the bones of a giant, or of a dragon, or of a beast drowned in the flood. The pattern is instructive because it shows how quickly evidence loses its meaning when the record of its origin is not kept alongside it. In the private cabinets of the 17th century, where shells, minerals, antiquities, and dried animals were arranged together, whale material at last sat beside a written catalogue. One consequence was the quiet end of a long-lived era. A physician and collector in Copenhagen, Ole Worm, was able to display and describe the skull of a narwhal with its long spiral tooth still in place, which settled the question of where the celebrated unicorn horns of European treasuries had come from. A single skull on a table did what no argument could, and the horn became a tooth. From those cabinets, the bones passed into institutions. Anatomical collections in London, Paris, Leiden, and elsewhere began to acquire cetacean skulls, jaws, flippers, and vertebrae, deliberately rather than by accident, seeking series of them for comparison. And surgeons with an interest in structure gathered parts of many species and published on what the parts had in common. The articulated skeleton hung from the ceiling of a public gallery, which is how most people now first meet a whale on land, belongs to the 19th century and to the museum, and it rests on two unglamorous centuries of burial pits, oil-stained floors, contested salvage rights, and hurried drawings made on cold sand. The difficulty was never a shortage of evidence. It was that the evidence lay inside, while the objection lay in plain sight. A whale seen from a boat is a smooth spindle moving through water, tapering to a tail, without a neck, without visible ears, without legs. And everything about its outline agrees with the outline of a fish. To argue that such an animal belonged with cattle and bats and mice required looking past the shape to the parts underneath it. And for most of recorded history, there was little occasion to look, since the animals were rarely available and the tools for opening them were the tools of the butcher. The first person whose observations survive in any detail understood the problem and answered it correctly. Aristotle, writing in the 4th century before the Common Era and drawing on the knowledge of Aegean fishermen along with his own examinations, recorded that dolphins and porpoises and the larger whales have no gills, that they take air through a single opening on the top of the head, that they must come to the surface or drown, that they bring forth living young rather than eggs, usually one at a time, and that the young are fed on milk from the mother's body. He noted that dolphins have a voice and can make sounds in air, and that the bones inside them are bone rather than the flexible material of sharks and rays. Having assembled these observations, he kept the cetaceans apart from the fishes in his descriptions, while acknowledging that they lived as fishes lived, which is about as much as could be honestly said before the internal anatomy had been drawn. That careful position did not travel well. Later compilers copied the striking details and dropped the reasoning, so the accounts that circulated through the Roman period and into the Middle Ages retained the spouting and the suckling as curiosities without drawing any conclusion from them. Practical life pushed in the same direction. Under the fasting rules observed across medieval Europe, meat from land animals was forbidden on many days of the year, while fish was permitted, and whale flesh, along with porpoise and dolphin, was generally counted as fish and eaten accordingly, sometimes as an expensive delicacy at high tables. A category that is useful in the kitchen and in the confessional acquires a durability of its own. And for several centuries, the whale was a fish, because there was no pressing reason for it to be anything else. The reopening of the question came from the dissecting table in the 16th century, in France, where two naturalists working on marine animals took dolphins apart and wrote down what they found. One of them described the lungs, the windpipe leading to the blowhole, and the internal arrangement that struck him as belonging to a land animal rather than to the fishes he had been cataloguing alongside it. And he recorded a pregnant female with an unborn young attached by a cord. The other described the same essentials, including the milk that could be pressed from the mother. And both men, writing books whose organizing principle was still the animals of the water, nevertheless left on the page the observations that would eventually dissolve that arrangement. Their work was not a reclassification. It was a set of accurate notes deposited where later anatomists would find them. In 1680, a London physician published a full anatomical account of a porpoise that had been taken in the Thames, working through it organ by organ in the manner then being applied to dogs and to human cadavers. The description covered the lungs and the diaphragm, the four-chambered heart, the arrangement of the stomach, the reproductive organs, and the brain, and its author remarked that the animal's internal structure resembled that of a quadruped, far more than that of a fish. This was a report on a single specimen, not a theory of classification, and yet it supplied precisely the kind of detailed comparison that classification would need, because it allowed the porpoise to be set item by item beside a land mammal, instead of beside a cod. Within a few years, an English naturalist working on the ordering of animals took that step formally. In his survey of the quadrupeds and serpents, published in the 1690s, he grouped the cetaceans with the viviparous quadrupeds on the strength of their internal characters, breathing with lungs, warm blood, live birth, and the nursing of young, and treated the absence of hind legs as a peculiarity of an otherwise ordinary mammal rather than as proof of fishhood. It was an argument from mechanism against an argument from appearance, and it did not immediately win. The great Swedish cataloguer of the 18th century, whose system of naming still governs zoology, placed the whales among the fishes in the early editions of his work on the system of nature, and only in the 10th edition, published in 1758, did he move them into the mammals, where they appear as a separate order alongside the primates, the beasts of burden, and the rest. That relocation, made in a book whose whole purpose was to be consulted, did more to settle the matter in ordinary practice than any single dissection. The anatomical case was then filled out by a London surgeon with a large private collection and a professional interest in comparative structure, who spent years assembling cetacean material from whaling crews and from strandings, and published his observations on the structure and economy of whales in the 1780s. He described the lungs and their capacity, the strong muscular arrangement around the blowhole and the valves that close it, the great vessels near the heart, the layer of fat beneath the skin, and the internal warmth of a freshly killed animal, which whalers already knew from working elbow-deep inside carcasses on cold water. He also examined the flipper, and this is where the identification became something more than a list of similarities. Inside the stiff paddle of a whale or a dolphin, beneath skin and dense connective tissue, lies a limb built to the standard plan of a land vertebrate. There is a short humerus at the shoulder, then a flattened radius and ulna, then a block of small carpal bones, and beyond them a spread of digits made of jointed phalanges, 4 or 5 fingers laid side by side like the ribs of a fan, sometimes with more finger bones in a row than any land mammal carries. The joints beyond the shoulder scarcely move, so the whole structure works as a single blade for steering rather than as a hand, but the bones are the bones of a hand in the same order, articulating in the same sequence. A skeleton in a gallery makes this visible to anyone walking past, which is one reason the mounted specimens of the following century did so much quiet teaching. The rest of the evidence accumulated steadily. Whalers and naturalists confirmed that a female whale carries a single calf, that it is born at sea and generally tail first, that milk is taken from paired openings recessed in slits on the underside of the body, and that whale milk is extremely rich in fat, thick enough to hold together briefly in seawater. Dissections showed rudiments of a pelvis embedded in the flesh well behind the ribs, unattached to the spine, sometimes with small additional bones beyond them. Remnants of a hind limb serving no locomotor purpose. Embryologists in the 19th century, examining unborn baleen whales taken from killed females, found tooth germs forming in the jaws of animals that would never grow a tooth, the buds appearing and then being reabsorbed before birth. Futile whales and newborns of several species were found to carry scattered bristles on the snout, hair on an animal otherwise entirely smooth. By then, the framework for interpreting such things existed in the form of the idea of homology, the recognition that the same bone can be identified across very different animals by its position and its relations rather than by its use, so that the finger of a bat, the toe of a horse, and the phalanx in a flipper are the same element put to different work. Under that principle, the whale stopped being an anomaly and became a mammal with an unusual address. And the interesting question shifted from what it was to how a body of that plan had come to be shaped for open water, a question that could not be answered from flesh at all, and would wait a long time for the right stones. The task of sorting followed naturally from the task of placing, and it proved harder. When the Swedish naturalist Carl Linnaeus set out his system in the 10th edition of his great Catalogue of Nature, published in 1758, he put the whales among the mammals and then divided them into only 4 genera: one for the narwhal with its single spiraled tooth, one for the sperm whale, one for the animals he called balaena, which took in the right whales and the rorquals together, and one for the dolphins, which absorbed the porpoises and the killer whale, and much else besides. It was a beginning rather than a description, a set of shelves with too few compartments, and it was built almost entirely from other people's accounts, from strandings, from the reports of whalers, and from the drawings and measurements that had accumulated in books over the previous 2 centuries. Linnaeus had never dissected a whale, and neither had most of the men whose names would soon be attached to whale species. The first great simplification came from the mouth. Whatever else varied, a whale either carried teeth or carried baleen, and no whale carried both in adult life, so the class fell cleanly into 2 divisions, the baleen whales on one side and the toothed whales on the other, and the split held up under every additional character that anatomists tested against it. The baleen whales proved to have paired blowholes, symmetrical skulls, no functional teeth after the embryonic stage, and enormously elongated upper jaw bones from which the plates of baleen hang. The toothed whales proved to have a single blowhole, skulls that are noticeably asymmetrical in the region of the nasal passages, and a functional set of teeth, sometimes numbering more than 200, sometimes reduced to a single erupting tusk, sometimes hidden in the gum, and never breaking through at all. Latin names were given to the 2 divisions in the middle decades of the 19th century, and the arrangement they express has survived every subsequent revision, which is unusual for a classification of that age. Below that first division, order arrived slowly and in a mess of duplicated names. The trouble was material. A naturalist working on beetles could hold the entire species in one hand and set 100 specimens side by side in a drawer, while a naturalist working on whales might have a skull, or part of a skull, or a jaw with 2 teeth, or a set of measurements taken hurriedly on a beach by someone who was not trained to take them, and very often only one such record from one animal in one ocean. Whales could not be collected in series. They could not be compared directly. Since no museum in the world could lay out 6 blue whale skeletons for inspection, and the specimens that did exist were scattered between Copenhagen and London and Paris and Philadelphia, so that comparison depended on drawings, on published measurements, and on letters between men who trusted each other's eyes to varying degrees. The result was an inflation of species names that took the better part of a century to deflate. A stranded rorqual on the coast of France, a rorqual skeleton in a Belgian collection, and a rorqual reported from the coast of Norway might each receive a separate name from separate authors in separate languages, when all 3 were the same animal at different ages. Age was itself a trap, since a young baleen whale differs from an adult in the proportions of the skull, in the color and length of the baleen plates, and in the number of vertebrae that have fused. And sex was another, since in several groups the males carry teeth or scars or head shapes that the females never develop. John Edward Gray, who catalogued the whale material at the British Museum through the middle of the 19th century, described a great many new species, and later revisers reduced a large proportion of them to synonyms, which is to say, to names for animals already named. This was not carelessness so much as the natural consequence of describing a wide-ranging group from single fragments. Every good monograph on cetaceans published after about 1880 spends a substantial part of its length untangling those synonyms, and some of the lists run to a dozen names for one animal. The characters that eventually proved reliable were mostly hidden ones. The bones of the ear, particularly the dense tympanic bulla, differ consistently between kinds and preserve well, so a single ear bone from a beach could be placed with some confidence. The count and arrangement of the throat grooves separated the rorquals, whose name comes from a Scandinavian word describing exactly those furrows, from the right whales, which have a smooth throat and a very different feeding posture. The number of baleen plates on each side of the mouth, their length, their color, and the coarseness of their fringe distinguished species within the baleen group. In the toothed whales, the shape of the skull and the position and number of teeth carried the weight, along with the form of the beak and the pattern of the nasal openings. Some of the resulting arguments were long and specific. The right whales gave particular trouble because the whalers of the Basque coast and later of Britain and New England had hunted a slow, thick, oil-rich animal in temperate Atlantic waters for centuries, while the whalers of the Arctic hunted another slow, thick, oil-rich animal among the ice, and both were called by more or less the same names in commerce. Anatomists working through the 19th century established that the Arctic animal, the bowhead, with its immense arched jaws and the longest baleen of any whale, was distinct from the temperate right whales, and that the temperate right whales of the northern Atlantic, the northern Pacific, and the southern oceans were closely related to each other and separable from the bowhead by the skull, by the plates, and by the callosities on the head. The southern and northern populations were argued over for a long time, treated sometimes as one species, sometimes as several, and the modern arrangement recognizes separate species in the northern Atlantic, the northern Pacific, and the southern hemisphere. The grey whale entered the catalogue from an unexpected direction, through bones dug out of shore deposits in Sweden, which were described as a distinct kind and named in honor of a Danish anatomist who had worked extensively on whales. Only afterwards was it recognized that the same animal was still alive on the far side of the world, in the shallow lagoons and coastal waters of the eastern Pacific, where American whalers knew it as an aggressive defender of its calves and called it names that reflected that experience. The bones and the living animal were matched. The name given to the fossil material stood, and the grey whale has been kept in a family of its own ever since, distinct from the rorquals and from the right whales in the structure of its throat, which carries only a few short grooves rather than the many long pleats of a rorqual. The beaked whales were, and remain, the least tractable part of the catalogue. Most of them live far offshore, dive deeply, surface briefly, and are rarely seen. So nearly all of them were named from strandings, and several are still known from only a handful of specimens. One of the first to be described in Europe came from a stranding on the Scottish coast at the very beginning of the 19th century, and through the following 100 years, a steady trickle of skulls from beaches in New Zealand, Australia, South America, Japan, and the Atlantic islands added species after species, distinguished chiefly by the size, shape, and position of the pair of teeth that erupt in adult males and stay buried in females. The group has continued to gain members into recent decades, occasionally from animals never observed alive. Industrial whaling, for all its destructiveness, supplied the series of specimens that comparative anatomy had always lacked. Shore stations and factory ships handled thousands of animals a year, and the scientists attached to them, working on flensing platforms with tape measures and notebooks, recorded lengths, sexes, fetal sizes, stomach contents, baleen counts, and earplugs in numbers sufficient to show what ordinary variation looked like within a species. Against that background, many of the doubtful names collapsed, and a few genuine distinctions emerged, including the recognition that what had been treated as one tropical rorqual was more than one kind. The catalogue that resulted is stable but not closed, and revisions continue, now with the help of genetic comparison, which occasionally divides an animal long thought single or joins two long kept apart. The two ways a whale can eat were known long before anyone understood either of them, because both were visible in the material that whaling brought ashore. From one kind of animal came slabs of dark, flexible plate, sold by weight and worked into stays and stiffeners, and from another came ivory teeth, carved by sailors on long voyages. That the two kinds of mouth belonged to two great branches of the same order of animals was clear enough by the 18th century. But the mechanics were another matter, and the accounts of how a baleen whale actually took food remained confused for a long while, partly because so few observers had ever watched one feed, and partly because the tissue itself resisted easy explanation. The word whalebone did not help. The plates are not bone and contain no bone, and when they were first examined closely, the guesses ran between horn, cartilage, and hair, with hair the closest of the three. Baleen is keratin, the same class of protein that forms nails, hooves, and horn sheaths, and it grows continuously from the palate, each plate rising from a bed of tissue in the roof of the mouth and hanging down like a stiff blade, with its flat faces set crosswise to the length of the body. The plates are arranged in two rows, one along each side of the upper jaw, hundreds of them in a large whale, and they are not solid slabs, but bundles of fine tubes embedded in a matrix of the same substance. As the outer surface wears away against water and food, the tubes are exposed at the inner edge and separate into a fringe of hair-like bristles, so that the working part of the apparatus is constantly being renewed from within. The fringe, not the plate, is what catches the food, and the mat formed by the overlapping fringes of many plates is what strains the water. The coarseness of that fringe varies from one kind of whale to another, and the variation matches diet closely enough that a naturalist handed a length of baleen can usually say what the animal was eating. Right whales and bowheads carry the longest and narrowest plates, with fringes so fine that they hold the small copepods that swarm in cold surface water. Animals only a few millimeters long, and those whales feed by swimming steadily forward with the mouth open, letting water pass in at the front and out through the sides, while the copepods accumulate on the inner surface. The Arctic whalers watched this from their boats, and one of them, William Scoresby, who combined a whaling master's experience with a naturalist's habits of description, set down an account of the Greenland whale's mouth and its skimming that remained the standard for decades. Rorquals have shorter, broader, coarser baleen, suited to krill and to shoaling fish, and grey whales have the shortest and stiffest of all, worn unevenly because they roll onto one side and plough the sea floor, taking in sediment and straining out the small crustaceans that live in it. Before those distinctions were drawn, older writers had explained the spout as water taken in at the mouth and driven out through the blowhole, which is why so many early drawings show a whale as a fountain. Anatomists dismantled that idea by following the nasal passages back to the lungs and showing that no channel connects the mouth to the blowhole in the way the story required, and the spout was reinterpreted as breath, warm and laden with moisture, condensing on release along with a film of water lying on the closed valves. The mouth, it turned out, was a filter and nothing else, and the water that entered it left again through the sides of the head or between the plates, never through the top. The Rorquals presented the harder problem because their method is not a steady strain, but a single enormous gulp, and the anatomy that permits it is unlike anything in other mammals. The throat and belly of a fin whale or a blue whale are pleated with deep longitudinal grooves that can unfold like the bellows of an accordion, and the two halves of the lower jaw are joined at the chin not by fused bone but by fibrous tissue, so that each side can rotate outward as the mouth opens. The tongue, which in a right whale is a firm structure that helps guide water, is in a Rorqual soft and capable of inverting into the expanding pouch beneath. When such a whale lunges into a patch of krill, it opens its jaws to something near a right angle. The drag of the water flings the mouth wide, the pleats stretch, and a volume of water at least as great as the whale's own body fills the cavity, after which the mouth closes and the water is forced out through the baleen while the food is held. The animal decelerates almost to a stop in the process, which is why the maneuver is repeated in short bouts and separated by climbs to the surface to breathe. Some of the finer points of this were only worked out once instruments could be attached to living whales, and later work on the nerves of the tongue and floor of the mouth showed them to be folded and elastic in a way that allows them to stretch to several times their resting length without tearing, which is what the geometry of the gulp requires. There is one more oddity in the baleen whales that took embryology to notice. The adults have no teeth at all, but their unborn young do, or at least they begin to. Tooth germs form in the jaws of a fetal Rorqual or right whale, small and simple and arranged in rows, and then they are resorbed before birth, leaving nothing behind, while the baleen begins to appear in the palate at about the same period. The observation was made on fetuses collected from killed females, and it carried an implication that was not lost on the naturalists who recorded it. Since an animal that builds and then discards teeth it will never use is most easily explained as the descendant of an animal that kept them. Among the toothed whales, the teeth themselves are simpler than in most mammals, and, in a way, less informative. They are usually alike from front to back, cones or pegs with a single root, without the division into incisors, canines, premolars and molars that lets a mammalogist read a land mammal's diet from a jaw, and they are not replaced, so that the set which erupts in a young animal must last its life. The numbers vary widely. Some dolphins carry well over 100, set in long, narrow jaws and interlocking when the mouth closes, which suits an animal that seizes single fish and squid and swallows them whole and head first. Sperm whales bear large conical teeth in the lower jaw alone, meeting sockets in the palate above. Beaked whales have reduced the set almost to nothing, a single pair erupting in adult males and remaining hidden in females, which cannot be a feeding arrangement at all and is generally read as a matter of contest between males whose heads and backs often carry paired parallel scars. The narwhal's tusk is a tooth of the upper jaw, spiraled and grown forward through the lip, borne chiefly by males. Whales with so few teeth still eat, and the study of how they do it turned attention from the teeth to the tongue and the throat. Sperm whales, beaked whales, pilot whales, and several others feed largely by suction, drawing the tongue back sharply to lower the pressure inside the mouth so that water and prey are pulled in, an action assisted in some of them by paired grooves on the underside of the head that allow the floor of the mouth to drop. Prey taken this way is swallowed intact, and because it is not chewed, the hard parts survive into the stomach, which is where much of what is known about the diets of deep-diving whales has come from. Stomachs opened on flensing decks yielded squid beaks by the thousand, sorted afterwards by species and counted, and among them were beaks of squid far larger than anything then held in any collection. Teeth also proved useful for a purpose unconnected with eating, since the dentine is laid down in layers that can be counted in a sawn and polished section, giving an estimate of age, and the parallel method in baleen whales was the counting of layers in the waxy plug of the ear canal. Sound behaves in water in a way that made the whole subject slow to arrive. It travels there about 4.5 times faster than in air. It carries much further before fading, and it crosses the boundary between water and air very poorly, so that a person standing in a boat with ears built for air hears almost nothing of what is happening a few meters below the hull, for most of the history of whaling and of whale study. Therefore, the sea was taken to be a quiet place, and the great animals in it were assumed to be mute, or at least to have no use for voices. The assumption was never examined closely, because there was no instrument with which to examine it, and it sat undisturbed alongside a good deal of accurate anatomy. There were hints, and they came mostly from people who spent nights on wooden vessels. Belugas gathered in northern estuaries produced whistles and squeals audible through a plank hull or a baled bucket, loud enough and varied enough that sailors gave the animal the name sea canary, a name recorded long before anyone made a recording. Whalers in small boats sometimes described a low knocking or a soft churring near a surfaced animal, and there were scattered reports of dolphins squeaking when lifted from the water, an observation old enough to appear in ancient natural history. None of this amounted to study. It was anecdote, unmeasured and unrepeatable, and it gave no way to say which animal had made which sound. The instrument came from war. Submarines made it necessary to listen underwater, and the hydrophone, a waterproofed microphone able to work under pressure, was developed and then improved through 2 conflicts, along with amplifiers, chart recorders, and eventually magnetic tape. Fixed listening stations were laid on continental shelves and in deep water, staffed around the clock, and their operators had one task, which was to distinguish the sound of machinery from everything else. Everything else turned out to be abundant. There were rasping choruses of fish that rose at dusk and continued for hours. There was the crackle of snapping shrimp over shallow bottoms, loud enough to mask an approaching vessel, and there were long, low pulses and trains of clicks that fitted no known category. Naval laboratories compiled reference catalogues of these biological sounds so that listeners could learn to set them aside. The catalogues, made in order to ignore the animals, became the first systematic descriptions of what the sea sounds like. After the middle of the century, the equipment reached civilian hands, and researchers at marine laboratories on the American East Coast began taking hydrophones out deliberately, in small boats, in search of whales rather than submarines. Recordings made at that time captured belugas in a northern river estuary, whistling and creaking and producing sharp, pulsed calls in overlapping streams. And the recordings were published with descriptions and with the frequencies measured. The practical difficulties were considerable. Engines had to be shut down, since a running propeller drowns everything, and the boat then drifted, and the cable had to hang clear of the hull to avoid the slap of waves, and the tape machines of the period were heavy, sensitive to damp, and limited in the range of frequencies they would record faithfully. Much early work was done with equipment that could not capture the highest sounds the animals were making, a limitation only recognized as recordings improved. The central problem was attribution. A hydrophone gathers sound from all directions and gives no picture, so a recording of a splendid series of clicks proves nothing about its author unless the author can be identified some other way. Researchers dealt with this in several ways at once. They recorded from single animals held in tanks, where the source was not in doubt. They worked with lone individuals at sea, watched from the surface while the tape ran, and noted the moment of a blow or a dive against the moment of a sound. They built arrays of several hydrophones spaced apart, so that the tiny differences in arrival time between them gave a bearing and later a position, allowing a sound to be placed on the water and matched with a visible animal. Slowly the sounds were assigned and the assignment held up. Alongside the hydrophone came a way of seeing sound. The sound spectrograph, developed in telephone research and then adapted for the study of speech and of birdsong, converts a recording into a picture, with time running along one axis and frequency up the other, and energy shown as darkness on the trace. Applied to whale recordings, it made visible what the ear could not easily hold: the exact shape of a rising call, the spacing of a click train, the repetition of one figure after another in the same order. Birdsong study had already built a vocabulary for such pictures, and whale researchers borrowed it, speaking of notes and phrases and syllables, and the borrowing carried some assumptions with it, but it gave the field a way to compare one recording with another on paper rather than from memory. Among the strangest of the unexplained naval signals were very low pulses near 20 Hz, at the bottom edge of human hearing, delivered in long regular series with silences between them. Going on for an hour or more, they were recorded at deep stations in more than one ocean, and their source was argued over before combined listening and sighting attributed them to fin whales, with related low moans and pulses belonging to blue whales. Sounds of that pitch travel exceptionally well in the deep ocean, particularly within the layer at middle depth, where temperature and pressure combine to bend sound rays back towards the axis and hold them there, so that a call can propagate for great distances with little loss. The consequences of that fact for the animals themselves are still being worked out, but its consequence for the science was immediate, because it meant a single instrument could hear whales that no eye on the surface would ever find. Sperm whales sounded quite different, and their voices were among the first to be recorded from identified animals in open water. They produce sharp broadband clicks, delivered singly at regular intervals during descent and hunting, and also in short patterned bursts, groups of 3 or 5 or more, clicks with distinctive rhythms, which were named codas and were noticed to pass back and forth between animals in a group. The steady clicking was soon interpreted as a means of ranging on the surroundings and on prey, a subject that belongs with the anatomy of the head, while the patterned bursts appeared to be social since they occurred when animals were together at the surface and were exchanged rather than emitted alone. Dolphins, easier to keep and to watch, yielded the largest early catalogues. Whistles that rise and fall in smooth contours, pulsed squawks and buzzes, and click trains varying in rate. Work with individually housed animals showed that each tended to produce one whistle contour far more often than others, a shape peculiar to the individual and stable over long periods. And this was described as a signature whistle, learned early and used most in circumstances of separation. The humpback recordings arrived through the Naval Listening Network as well. An engineer at a station in the Western Atlantic had accumulated tapes of long, complex utterances made near the island in winter, and passed them to researchers who set about analyzing them with spectrograms. What the pictures showed was hierarchy and repetition. The smallest elements, the single moans, groans, whoops, and ratchets, occurred in fixed, short sequences, and those sequences were repeated a number of times before giving way to the next kind, and the succession of kinds ran in a consistent order. And when the last was finished, the whole sequence began again. A complete cycle lasted a matter of minutes, and an animal might repeat it, with little variation, for many hours. The terms adopted were units, phrases, themes, and song, and the singers were found to be lone males on the winter breeding grounds, hanging head down in the water with the flippers spread. Later work added the property that has occupied the field since. The song does not stay the same. Small alterations appear in one theme, spread through the singers of a population within a season, and accumulate year after year until the song of a decade later bears little resemblance to the earlier version, while at any one moment the animals of a given ocean basin are singing very nearly the same thing. The clicks had been on the tapes from the beginning. Anyone who lowered a hydrophone near a school of dolphins heard them, sharp and dry, sometimes in long even trains, sometimes accelerating into a sound the early listeners compared to a creaking door or a rusty hinge. And for a while they were catalogued alongside the whistles as simply another noise these animals made. What the clicks were for took longer to establish, and the answer arrived by an indirect route, through bats. In the early 1940s, two researchers in the United States, Donald Griffin and Robert Galambos, demonstrated that flying bats emitted ultrasonic pulses and used the returning echoes to detect obstacles and insects, and gave the ability a name, echolocation. The idea that a mammal could form a usable picture of its surroundings from reflected sound was suddenly not a speculation, but a described fact, and it was available to be applied elsewhere. Some of the groundwork had already been laid without anyone drawing the conclusion. A curator at an oceanarium in Florida, Arthur McBride, had written notes in the late 1930s describing how bottlenose dolphins behaved when a seine net was drawn through turbid water at night, avoiding the net where it was slack and finding the gaps. And he had compared their performance to that of bats. Those notes sat in a file for years before they were published, by which time others had reached the same place by experiment. The experiments were done at a laboratory in Florida by Winthrop Kellogg, who had two dolphins in a large enclosure of murky water and set them problems. He hung vertical rods and metal plates in their path and found they threaded through without contact, even in water so clouded that a person could see nothing at arm's length. He offered fish of different kinds and found the animals could distinguish them at a distance before any contact. He dropped a fish into the water at a random moment and recorded the burst of clicks that preceded the animal's arrival, and he showed that the click trains began before the approach and became faster as the distance closed. In the same years, William Cheval and Barbara Lawrence, working at a marine laboratory in the Northeast, ran comparable trials and recorded the sounds with better equipment, establishing that the clicks were brief, broadband and directional, and that they were produced in trains whose interval shortened as the animal neared its target. The two lines of work together made the case that toothed whales were doing with water what bats did with air. The most careful demonstration came a little later from Kenneth Norris and his colleagues, who trained a bottlenose dolphin to accept soft rubber suction cups placed over both eyes. Deprived of sight entirely, the animal swam a course among vertical pipes without touching them, located and retrieved dropped fish, and learned to discriminate between targets that differed only in material or in wall thickness, clicking steadily throughout. The same group noticed something about the geometry of the performance. When the animal scanned, it moved its head, and the sound field measured around it was not uniform. The beam went forward and slightly upward from the forehead, narrow, and it did not come out of the open mouth as some had assumed. Whatever generated the clicks lay above the palate, and whatever shaped them lay in the bulging front of the head. The bulge is the melon, a mass of fatty tissue that sits over the upper jaw and gives the smaller toothed whales their rounded profile. And it turned out to be neither muscle nor blubber, but a specialized body with an unusual composition. Analyses of its lipids showed that they differ from ordinary fats and differ from place to place within the melon itself, with the inner core containing compounds through which sound travels more slowly than in the surrounding layers and in sea water. A gradient of sound speed is what an acoustic lens requires. Sound entering the core is bent as it passes outward, and the effect is to collect the energy leaving the nasal region and send it forward as a beam rather than allowing it to spread in all directions. The concave front face of the skull, dished behind the melon, and the air spaces around it contribute by reflecting sound forward that would otherwise be lost backwards into the body. The source of the clicks proved to lie in the nasal passages, which in toothed whales are among the most rearranged structures in mammalian anatomy. The blowhole sits on top of the head, and beneath it the passages run down towards the throat in a complicated arrangement of muscular valves, plugs and air sacs, and along the way, at a point below the blowhole, each passage carries a pair of tough lips of tissue set into the wall, held together by muscle. Later anatomists, working with scanning techniques and with fresh material, described these paired structures and the small bodies of fat that lie against them. And the model that emerged is one in which pressurized air is forced past the closed lips, causing them to slap together and release a pulse into the adjacent fatty body, from which it passes into the melon and out through the forehead. The air is not exhaled but shunted between the sacs and recycled, which is why an animal can click continuously through a long dive without releasing bubbles. Many toothed whales are asymmetrical in the skull and in the soft nasal anatomy, with the passages of one side larger than the other. And the working idea is that one side has been specialized for sound production while the other retains the business of breathing. The sperm whale carries the same system enlarged beyond all comparison with its relatives, and its head occupies about a third of the body length. Inside are two great fatty organs, one above the other. The upper is the spermaceti organ, a case of liquid wax. Below it lies a layered body of fat and connective tissue, long known to whalers as the junk. The nasal passage of the left side runs forward under the skin to the blowhole at the tip of the snout, while the right passage runs back through the pair of organs and ends at a valve complex near the front of the skull. Norris and a colleague proposed that a pulse generated at that complex travels backwards through the spermaceti organ, reflects from an air sac at the concave front of the skull, returns forward through the layered junk, and leaves the front of the head as a beam. And this bent path through the head is the reason the animal's clicks are among the loudest and most sharply directed sounds produced by any animal. Recordings made from tags fixed to diving sperm whales have been consistent with a source at the front of the snout, and with the long delays that a two-way passage through such a head would introduce. Reception is the other half, and it works nothing like an ordinary mammalian ear. The external ear canal in toothed whales is narrow and largely useless, and the middle and inner ear bones are packed into a dense complex that is not rigidly fused to the rest of the skull, but suspended in a cushion of tissue, isolated from the bones that carry the animal's own vibrations. Sound reaches the ear instead through the lower jaw. The rear part of each mandible is hollow and thin-walled, thin enough in places to admit light when held up, and this pan of bone lies against a channel of fat that runs backwards to the ear complex. Experiments in which small sources were touched at points around the head of a trained animal, and in which nerve responses were measured, both indicated that sensitivity was highest at the lower jaw and along that fatty pathway, and later work suggested that the throat region also transmits sound inward. The hearing that results extends far above the human range, into frequencies of over 100 kHz in many species. Behavior recorded by tags has since filled in how the system is used at sea. An animal searching produces widely spaced clicks, and as it converges on prey, the interval shortens until the individual clicks merge for the listener into the rasping buzz that the early experimenters had heard in their tanks. And the buzz continues to the moment of capture. The intensity is adjusted as the target nears, so that the returning echo stays within a workable range, and the beam can be narrowed or widened. Beaked whales, hunting 1,000 meters down in permanent darkness, begin clicking only after they have descended past a certain depth, fall silent on the way back up, and appear to do all of their finding and catching with sound alone. For most of the history of the subject, a whale seen at sea was a member of a species, and nothing more particular than that. A ship's log might record a certain number of finbacks or a school of blackfish, and the entry closed there, because there was no reason to think the animal in front of the observer could ever be told apart from the next one of its kind. What changed that was not a new instrument so much as a new habit of looking, combined with a camera that was cheap enough to use freely. Once photographs could be taken by the hundred from a small boat and compared later at leisure, the marks that had always been on the animals became usable, and the whale stopped being a type and became somebody in particular. The right whales made the point most plainly, because they carry pale patches of roughened skin on the head, above the eye, along the lower lip, and in a cluster on the rostrum. And these callosities appear whitish or cream-colored because they are colonized by small crustaceans that live nowhere else. The arrangement of the patches differs from one animal to the next, and it settles into its adult form within the first months of life and then stays essentially unchanged. Researchers working in the sheltered gulfs of the Argentine coast in the early 1970s photographed the heads of southern right whales from cliff tops and from the air, drew the patterns as diagrams, and found that they could sort a season's photographs into individuals and then find the same individuals again the following year and the year after that. Humpbacks offered a different marking on the underside of the tail. When a humpback dives, it often lifts its flukes clear of the water, exposing a surface that ranges from almost entirely black to almost entirely white, with mottling, streaks and scars in between, and with a trailing edge nicked and scalloped in ways that persist for life. Photographs of raised flukes taken on the feeding grounds of the Gulf of Maine were matched against one another, then against photographs from Newfoundland, from Iceland, from the banks near the West Indies, and the matches accumulated into a catalogue held in common. An animal photographed in a bay in New England in one summer could be shown to have been in the tropics in winter and to have returned to the same bay in later years. Killer whales are identified by the shape of the dorsal fin, which in adult males grows tall and often acquires nicks along its rear margin, and by the grey saddle patch behind it, whose outline and pigmentation vary considerably. A long study begun in the coastal waters of British Columbia and Washington in the early 1970s gave each animal a number, sorted the numbers into family groups, and repeated the census annually. Because the same waters were surveyed year upon year, and the population was small enough to be counted almost in full, the record became something close to a genealogy, with births noted in the season they occurred, mothers and offspring linked by constant association, and disappearances taken as deaths. Females followed since the beginning of that work were still being photographed decades later. Other species yielded to the same approach with their own features. Sperm whales are told apart by the trailing edge of the flukes, notched and sometimes deeply scarred. Bottlenose dolphins are identified by the notches in the dorsal fin, and a study in a shallow bay on the Gulf Coast of Florida has followed successive generations of a resident community in this way. Blue whales carry mottled grey pigmentation along the flanks that is distinctive in the region behind the blowholes and below the dorsal fin, and finbacks bear a pale chevron across the back, and an asymmetrical light patch on the right side of the jaw. Grey whales are recognized by the pattern of pale barnacle scars and blotches on their mottled skin. In each case, the useful mark had to be found, tested for stability over years, and photographed from a consistent angle. The method that made all of this quantitative was older than the photographs and came from the study of birds and fish. If a proportion of a population is marked, and a later sample is examined for marks, the ratio between marked and unmarked animals in the second sample carries information about the size of the whole. Photographic identification is a form of marking in which the animal supplies the mark, and the researcher only records it, and so the same arithmetic applies. From matched photographs came estimates of population size, of the rate at which adults survive from 1 year to the next, of the interval between a female's calves, which in humpbacks commonly falls at 2 or 3 years, and of the age at which females first give birth. None of these figures could be obtained from a single encounter, and all of them fell out of encounters repeated over long spans. There was an earlier tradition of marking that did not involve photographs at all. In the 1920s and 30s, investigators working from a research vessel in the Southern Ocean fired numbered metal darts into the blubber of whales from a modified gun, with the intention that the dart would remain embedded, unnoticed by the animal, until the carcass was cut up at a shore station or on a factory ship, at which point the flensers would find the metal and return it with a note of the place and date. The returns were few relative to the marks placed, and they came only from animals that were killed, but each one drew a straight line on the chart between 2 known positions and 2 known dates. And those lines were the first hard evidence about where particular whales went. Radio telemetry followed, at first with transmitters whose signal had to be picked up by a receiver within line of sight, which tethered the researcher to the whale and limited the work to days or weeks. The step that widened the picture was the use of satellites to relay position data, so that a transmitter attached to a whale could send a brief signal each time it surfaced, and that signal could be received in orbit and the position calculated from the shift in frequency as the satellite passed. Tags of this kind, small cylinders anchored in the blubber and dense muscle near the base of the dorsal fin and applied from a boat with a crossbow or a compressed air launcher, have stayed attached for weeks and in some cases many months, and have traced individual whales across whole ocean basins. A second family of tags is designed to come off. A housing carrying pressure sensors, accelerometers, magnetometers and hydrophones is held to the skin by suction cups, records in fine detail for a period of hours, releases, floats to the surface, and is recovered by radio direction finding. These are the instruments that produced the descriptions of clicking on descent and silence on the ascent, along with the fluking rate, the body angle, the gliding portions of a dive, and the sounds the animal makes and hears. They give depth and posture second by second for 1 day, where satellite tags give position roughly for a season, and photographic catalogues give a handful of points spread over a lifetime. The 3 scales are complementary rather than competing. Alongside the images came small samples of skin and blubber, taken with a light dart that bounces off the animal, from which sex can be determined and an individual genetic profile obtained. A genetic identity does not fade or heal, and it can be matched to a photograph of the same animal on the same day. So the 2 catalogues reinforce each other and allow parentage to be worked out among animals that were never seen together. The photographic collections themselves have grown into shared archives, first as filing cabinets of prints sorted by fluke pattern or fin shape, later as digital databases with computer-assisted matching, and more recently with automated comparison that scans a new image against many thousands of old ones and offers candidate matches for a human eye to confirm. The cumulative effect has been to change the unit of study. Questions that once concerned averages for a stock now concern the histories of named animals, which feeding ground a female uses and whether her daughter uses the same one, how often an individual is scarred by fishing gear and whether the scars accumulate, how long a particular whale lived, and how many calves it raised, and how far it traveled between the place it fed and the place it bred. Some of the individuals first catalogued in the 1970s are still being photographed, which means that the record for a few whales now covers most of a human working life, and rather less than a whale's. The pattern that emerged from all this individual tracking was not new in outline. Whalers had known for centuries that whales arrived and departed on a schedule, that certain bays filled with them in one season and emptied in another, and that a ship could plan a year around those appearances. What the long records did was turn that working knowledge into geography, drawing lines on charts where before there had been only expectations of presence and absence, and the lines proved longer than most naturalists had assumed. The grey whale of the eastern North Pacific gave the clearest early picture, partly because it travels close to shore and can be watched from land. It feeds in summer in the shallow northern seas, on the muddy shelves of the Bering and Chukchi seas and beyond, where it ploughs the sediment for small crustaceans and leaves trails of disturbed mud behind it. And in autumn, it moves south along the coast of North America, past Alaska and British Columbia, past Washington, Oregon, and California, until it reaches the warm, shallow lagoons on the Pacific side of the Baja California Peninsula. There, the calves are born, in water so shallow and so enclosed that a 19th century whaling captain who found the lagoons was able to hunt within them. And the same captain later wrote a careful account of the animals and their habits that remains one of the earliest descriptions of the migration as a whole. The round trip, made twice a year, amounts to many thousands of kilometers, and it is undertaken largely without feeding on the reserves laid down during the northern summer. Because the route runs so near the coast, it became possible to count the whales as they passed. Observers stationed on headlands in central California, working in shifts through the winter months, recorded every animal that swam by within sight of shore, noting direction, group size, and whether a calf was present. And by repeating the exercise season after season, a series of estimates was built that stretches across decades. The counts revealed structure inside the migration. Pregnant females tend to move south early, as though timing their arrival for birth, followed by other adults, and on the northward journey, the mothers with new calves come last, traveling slowly and very close to the beach, sometimes inside the line of breaking surf, where the water is too shallow and noisy for killer whales to hunt easily. Humpback whales presented a harder problem because their journeys cross open ocean rather than following a coast, and because they gather in tropical waters in groups that mix animals from widely separated feeding grounds. Whaling records supplied the first sketch, catch positions and dates, entered in logbooks over many years and later assembled from national and international registries, showed humpbacks in high latitudes during the local summer and in warm, shallow waters during the local winter, and the seasonal reversal between the two hemispheres was plain in the same data, since the northern and southern populations occupy their respective tropics half a year apart and do not meet at the equator. More precise links came from marking. In the 1920s and 30s, a series of British expeditions to the Southern Ocean fired numbered metal darts into the blubber of whales, in the expectation that the marks would be recovered later when the animals were processed at a whaling station or a factory ship. Most were never seen again, and the ones that were recovered arrived as a serial number attached to a place and a date, with nothing in between. But even that scattering of paired points established that whales caught off the coasts of Africa, Australia, and South America in winter belonged to the same populations that fed near the Antarctic ice in summer. The method was crude, and it depended on the industry that the research was meant to regulate. Yet it produced the first hard evidence that the two halves of the annual cycle belong to the same animals. Photographic identification replaced the darts with something gentler and far more productive. A humpback photographed on a feeding ground off the coast of Alaska and photographed again, months later, in the shallow water around the Hawaiian Islands establishes the link without touching the whale at all. And thousands of such matches, assembled by comparing catalogues held on opposite sides of an ocean, gradually resolved the North Pacific into a set of feeding areas and a set of breeding areas connected by a web of routes rather than by single lanes. Some links proved strong and some weak. Whales from one feeding region turned up overwhelmingly at one archipelago, while whales from another spread across several breeding grounds, and a few individuals appeared in places that no model had predicted, including movements between breeding grounds in different ocean basins. Satellite tagging then filled in the space between the endpoints. A transmitter anchored in the blubber and muscle of the back, small enough to be carried without evident hindrance, sends brief messages to polar orbiting satellites whenever the whale surfaces. And from the timing of those messages, a position can be calculated. The resulting tracks are not smooth, since a tag reports only when the animal is at the surface and the satellite is overhead, but they show what the paired sightings could not. The heading a whale holds, how straight it swims, where it pauses, and how far it strays from the shortest path. Humpbacks crossing to tropical waters were found to hold courses of remarkable consistency across days of open ocean, correcting for currents and wind in a way that suggests they are not simply following a coastline or a temperature gradient. Grey whales fitted with tags in the western North Pacific, near the island of Sakhalin, produced one of the more unexpected results. When an animal from that small population crossed the northern Pacific and traveled down to the Mexican lagoons and back, a journey longer than any previously documented for a mammal, and one that raised the question of whether the western animals are a separate population at all or partly the same whales seen at a different point on their route. Other species turned out to migrate in ways that fit the pattern loosely or not at all. Blue whales in the eastern North Pacific were tracked from waters off California and Baja California to productive open ocean areas nearer the equator, moving between feeding opportunities rather than between feeding and calving grounds in the strict sense. And their movements shift from year to year with the distribution of their prey. North Atlantic right whales were found to spend summer and autumn in the cool waters of the Gulf of Maine and the bays north of it, and to calve in winter in the warm, shallow water off the southeastern United States, though a considerable number of individuals go missing from the record for months at a time and are presumed to be somewhere that no one is looking. Bowhead whales do not leave the Arctic at all, but move with the seasonal advance and a retreat of the ice, spending the winter in areas of broken pack and following the leads north as they open. Sperm whales divide their movements by sex rather than by season, with females and young remaining in warm and temperate waters year-round, while mature males travel to high latitudes and return. There are also populations that have largely given up the journey. Humpbacks in the Arabian Sea appear to remain in those waters through the year, breeding and feeding in the same region, taking advantage of a seasonal upwelling that brings cold, productive water to low latitudes, and genetic work indicates that they have been isolated from other humpbacks for a long time. Their existence complicates any explanation that treats the long migration as a necessity rather than as one strategy among several. The explanations offered for the pattern remain partly open. The feeding grounds are cold and seasonally productive, and the breeding grounds are warm, sheltered, and comparatively empty of food. So the whales are trading months of fasting for something that the warm water provides. A newborn calf is thin-skinned and poorly insulated, and loses heat quickly, which argues for warm water as a nursery. Killer whales are more numerous in some regions than others, which argues for shelter. The energetic cost of molting and skin maintenance in cold water has also been proposed as a factor. What the tracks and the catalogues establish is not the reason, but the fact in detail sufficient to say when each population moves, along which corridors, and with what regularity from one year to the next. For most of the time that people have watched whales, the deep part of a whale's life was simply absent from the record. A sperm whale seen from the deck of a ship was a back and a spout, and then a raised fluke, and after that a stretch of empty water lasting the better part of an hour, and whatever happened in that interval had to be inferred from what the animal brought back with it, or from what could be recovered after death. Whalers knew that the sperm whale went down a long way, because a harpooned animal could take out an extraordinary length of line, and because the stomachs of the whales they cut open held the beaks and fragments of squid that belonged to no surface community. The evidence was indirect but consistent, and it accumulated over a century and a half into a settled expectation that this was an animal of the deep water, feeding somewhere well below the reach of light. A more precise clue arrived from the industry of laying cable across the ocean floor. On a number of occasions, when a broken submarine telegraph cable was hauled up for repair, a dead sperm whale came up entangled in it, wrapped about the jaw or the flippers, and the depths at which some of these entanglements occurred were considerable, in cases well beyond 1,000 meters. Each recovery was an accident, and the whales concerned had made a fatal error. But the accidents were informative in a way that no sighting could be, because a cable lies on the bottom and its position is known. The record they built up implied a whale that came into contact with the sea floor at depths where the water is close to freezing and entirely dark. The instruments that eventually replaced inference were adapted from work on seals. Pressure-sensitive recorders, small enough to be carried by a diving animal storing a trace of depth against time, had been developed for use on ice-breathing seals. And once the principle was established, the problem for whales was attachment rather than electronics. Suction cups pressed against the skin from a small boat, sometimes on the end of a long pole and sometimes fired from a crossbow, will hold a package of sensors for a few hours or a few days before the tag releases, floats, and is recovered by radio signal. A parallel line of evidence came from listening. A sperm whale echolocates almost continuously through its descent and its search, and an array of hydrophones can place the source of those clicks in 3 dimensions, so that a dive can be reconstructed without touching the animal at all. What the traces showed for sperm whales was a routine of long, repeated, businesslike descents. A foraging dive commonly reaches something between 400 and 1,000 meters and lasts around 3/4 of an hour, followed by 8 or 9 minutes at the surface, breathing steadily before the next descent begins. Deeper dives occur past 1,000 meters and beyond, and the pattern varies between regions and between the sexes, with large males in high latitudes making the most extreme profiles. The descent itself is efficient rather than labored. The whale sinks with little tail movement over much of the way down, because compression of the air spaces makes it denser as it goes, and it glides, converting the effort saved into oxygen conserved. Beaked whales turned out to be the more extreme divers, which was unexpected mainly because they had been so little observed. There are more than 20 species in the family, several of them still known largely from stranded bodies and a handful of sightings, and they are undemonstrative at the surface, showing little of themselves and rarely gathering in large groups. When tags were placed on Cuvier's beaked whales and Blainville's beaked whales in deep water off the Canary Islands and in the Bahamas, the profiles that came back described dives lasting an hour or more as a matter of routine, reaching depths beyond 1,000 meters, and interspersed with series of shallower dives in which the animals appeared not to feed. Later records extended the extremes considerably, with individual Cuvier's beaked whales tracked to depths close to 3,000 meters, and in one case, remaining submerged for more than 3 hours. Those figures come from a small number of animals and may not describe the ordinary working day of the species, but they set the outer edge of what a breathing mammal has been shown to do. The tags also revealed a pattern in when these whales use sound. On the way down, they are silent for the first 100 or 200 meters and only then begin to click, and they fall silent again well before returning to the surface, ascending quietly and often at a distance from where they went down. The interpretation generally offered is avoidance of killer whales, which hunt near the surface and which can hear a clicking whale. A deep diver that says nothing in the upper layer is harder to find. It is a behavioral solution to a problem of exposure rather than a physiological one, and it shapes the acoustic record in a way that took some time to understand, because a silent animal is easily missed by surveys that listen rather than look. The physiology that supports these absences from the air is not built on a single trick, but on a set of adjustments, most of them shared in some degree with seals and with diving birds. The first is where the oxygen is kept. A deep diving whale does not rely on a large lungful. Its lungs are modest relative to its size, and the greater part of its usable oxygen is bound in the blood and in the muscle. The blood volume is large, the concentration of hemoglobin is high, and the muscle is loaded with myoglobin to a degree that turns it very dark, almost black in the deepest divers, so that the working tissue carries its own store and can draw on it locally. The chemistry of these myoglobins has been examined closely, and the molecules of deep diving species carry surface charges that let them be packed at high concentration without clumping together, which is one of the quieter findings in the field and one of the more satisfying. The second adjustment is the redistribution of what is carried. On submerging, the heart slows, sometimes to a small fraction of its surface rate, and the vessels supplying muscle, skin, gut, and extremities constrict, so that circulating blood is directed toward the heart and the brain, the two tissues least tolerant of interruption. The working muscles are left to consume their own myoglobin-bound oxygen and to accumulate the products of anaerobic metabolism if the dive runs long, which are flushed and cleared during the interval at the surface. Heart rate recordings from tagged animals have shown how deep this bradycardia can go, and how it is modulated during a dive rather than simply switched on, with brief accelerations that appear to accompany bursts of activity. The third concerns gas and pressure. The airways of these whales are stiffened with cartilage well down into the smaller branches, and the chest wall is compliant, so that as pressure rises, the alveoli empty and collapse in an orderly fashion, pushing air back into the reinforced passages where it cannot readily be absorbed into the blood. The effect is to limit the amount of nitrogen taken up at depth, which is the same problem that troubles human divers, and it is a mechanical solution rather than a chemical one. It is not, however, a complete solution. Examination of sperm whale skeletons has found pitting and lesions in the bone of the sort that in human patients is associated with nitrogen bubbles, suggesting that these animals live with a degree of gas stress that they manage rather than avoid. That finding acquired a wider significance after a series of beaked whale strandings coincided in time and place with naval exercises using mid-frequency sonar. Some of the animals examined showed gas and fat emboli and hemorrhage around the ears and elsewhere, injuries consistent with bubble formation, and the working explanation is that a disturbed whale abandons its normal ascent behavior and surfaces in a way that its physiology does not accommodate. The mechanism is still argued over in its details, and the number of animals available for examination has always been small, but the episode changed how deep diving was understood, from a set of capacities to be admired into a set of narrow tolerances that can be exceeded. The recognition that whales were mammals carried an implication that took much longer to follow up, because a mammal with lungs and milk and finger bones inside its flipper is not a creature that could have begun in the sea, and somewhere in the past there had to be ancestors that walked. For most of the 19th century, that implication remained a matter of reasoning rather than evidence, and the fossils that did come to light were not obviously transitional. In 1834, an American naturalist gave the name Basilosaurus to a set of enormous vertebrae recovered from the soft rocks of the southern United States, and the name, which means king lizard, records his belief that the animal had been a marine reptile of some kind. Teeth and other material sent to Richard Owen in London persuaded him otherwise, since the double-rooted, two-crowned cheek teeth belonged to a mammal rather than a reptile, and he proposed the alternative name Zeuglodon in acknowledgement of that, the older name held by the ordinary rules of priority, so that one of the first fossil whales ever described still carries a title that misidentifies it entirely. The rocks that would eventually yield the fuller story lay along the southern margin of a vanished sea. During the Eocene, roughly between 55 and 34 million years ago, a broad, warm ocean called the Tethys separated the northern continents from Africa and from the drifting fragment of land that would become India, and its shallow shelves and estuaries and lagoons accumulated the sediments in which early whales were buried. Two stretches of that former coastline have proved unusually generous. One lies in the desert southwest of Cairo, in the Fayum Depression of Egypt, and the other in the dry hills of northern Pakistan and neighboring parts of India. where marine and river sediments of the right age are exposed at the surface and weathered clean. The Egyptian site is now known as Wadi al-Haytan, the Valley of Whales, and it was being worked by European expeditions in the early 20th century, when German and British collectors described skeletons of Basilosaurus and of a smaller, more conventionally proportioned relative named Dorudon. These animals were fully aquatic. Their nostrils had already migrated back from the tip of the snout, their forelimbs were flippers, their necks were short, and their tails were built for swimming. Basilosaurus in particular had extraordinarily elongated vertebrae, so that a body perhaps 15 or more meters long was mostly a chain of stretched bones, giving it a serpentine shape unlike any living whale. What the early expeditions did not find, or did not recognize, were the hind limbs, and it was later work in the same beds, carried out from the 1980s onward, that recovered small but complete hind legs with knees, ankles and toes, attached to a pelvis and standing perhaps a few tens of centimeters from the body of an animal many meters long. They were far too small to bear weight on land, and their function, if they had one, is uncertain, but they preserved the whole architecture of a walking limb in an animal that had not walked for millions of years. The site was inscribed as a World Heritage Property in 2005, in part because the skeletons lie where they were buried, in the sequence in which they were laid down. The Pakistani rocks are older, and they contain the earlier chapters. In 1981, a partial skull collected from beds in the Kohat and Potwa region was described under the name Pachycetus, and its claim to be a whale rested largely on its ear, the bone that houses the middle ear in cetaceans. The tympanic bulla carries a thickened, dense, in-rolled lip on its inner side called the involucrum, and that feature is found in whales and in nothing else. Pachycetus had it. The rest of the skull, however, was that of a long-snouted land mammal, with a narrow brain case, eyes set high on the head, and a full set of differentiated teeth suited to seizing and slicing rather than to filtering. Later, collecting produced enough of the skeleton to show a slender animal about the size of a wolf, with 4 functional legs, running on land or wading in the shallows of rivers and estuaries, and hearing in the ordinary way through air. In 1994, a second Pakistani animal was described from beds slightly younger and named Ambulocetus natans, the walking and swimming whale. Its proportions were those of a large, heavily built, short-legged creature with an elongated skull and very large hands and feet. And the joints of the vertebral column suggest that it moved in the water by undulating the back and driving with the hind feet, in the manner of an otter rather than a fish. On land, it would have been awkward, capable of hauling itself about, unlikely to travel far. Between that stage and the fully marine basilosaurids, several families fill in the intervals, all of them known chiefly from the Tethyan margin. The Remington achetids had absurdly long, narrow snouts and small eyes, and appear to have hunted in murky water. The protoceatids include Rhodocetus, with a shortened pelvis, a mobile spine and hands and feet still bearing separate digits, and Myacetus, described in 2009 from Pakistan, a specimen preserved with a single fetus inside it, positioned head first in the way that land mammals are born, rather than tail first as living whales are. The inference drawn was that these animals still came ashore to give birth, and that the sea had not yet claimed the whole of the life cycle. The most persistent argument concerned not the sequence itself, but the point at which it joined the rest of the mammals. Anatomists working on the teeth and skulls of the earliest whales had long allied them with an extinct group of archaic hoofed carnivorous mammals, the mesomniscids, and the resemblance was real enough. Molecular biologists working on living animals kept arriving somewhere else, at the artiodactyls, the even-toed hoofed mammals, and more precisely at the hippopotamuses as the nearest living relatives of whales. The disagreement was settled by a bone in the ankle. Artiodactyls possess a distinctive astragalus with a pulley-shaped surface at each end, a double-pulleyed shape found in no other group, and when reasonably complete feet of Rhodocetus and of a Pachycetid were described around the turn of the century, the astragalus had precisely that form. The bones and the molecules were describing the same relationship, and whales took their place inside the artiodactyls rather than beside them. The land end of the sequence was extended further in 2007, with the description of Indohyus, a small deer-like animal from Kashmir belonging to a family called the Rowellids. It was about the size of a cat, with slender legs and unremarkable teeth, but its ear bones carried the involucrum, and the walls of its limb bones were unusually thick and dense, a condition seen in living mammals that spend time walking on the bottoms of streams rather than swimming at the surface. Measurements of oxygen and carbon isotopes in its teeth pointed in the same direction towards a life spent substantially in fresh water, perhaps feeding on land and retreating to water for safety. Isotopes have been used across the whole sequence in the same way, and the pattern they show is a gradual shift from the freshwater signatures of the Pachycetids through the mixed values of the Protoceratids that evidently moved between estuaries and the open sea to the fully marine values of the Basilosaurids. What the fossils show, taken in order, is not a single change but a long series of them, arriving at different times. The nostrils travel back along the top of the skull. The neck shortens and stiffens. The tail vertebrae broaden where a fluke would attach. The pelvis loses its firm connection to the spine and the hind limb dwindles. Inside the head, the ear is rebuilt for water. The bulla becomes denser and more isolated from the skull, and a channel of fat develops in the lower jaw. By the end of the Eocene, the last of the Basilosaurids overlap with the earliest members of the two modern groups, the baleen whales and the toothed whales, both of which appear as small forms in southern waters, some of them still bearing teeth in jaws that would later hold baleen, and others with skulls already reorganized around the production and reception of sound. The sequence was assembled from many hands over more than a century and a half, from quarry workers and desert surveys and museum drawers, and it is ordered not by the neatness of the story, but by the order of the rocks. We are going to stop here. The music will carry on for a while, and then it will fade on its own. There is nothing more to do tonight. Rest well, and see you very soon.